So Module 18G, we're wrapping up our discussion about titration. A little bit more looking at titration curves, being able to predict what type of substance we are titrating based on the way the curve looks, understanding the relationship between the pKa and the species in solution, predicting key species in solution at various points in a titration, and just doing two last examples of pH calculations involving titration curves. First, let's talk about pKa. What is pKa? We know mathematically that pKa just means negative log of Ka. That's great. But what does that really mean? Well, here's the thing. Remember what a Ka is. A Ka is a way for us to express how much of a substance is actually going to dissociate in solution. And so we use that to measure how likely is it for a substance to give up a proton. The larger that Ka value, the more likely it is to give up its proton. Cool. But those numbers get pretty small, and they're kind of hard to deal with that way for most of us to think about. Like, most of us don't think in scientific notation. So instead, we develop the P scale, or what we do like for pH, we do for pKa as well, where we take the negative log of that substance, and it takes that small number, and it makes it big. So it makes it easier for us to deal with. So when we talk about pKa, we can say the smaller the pKa value, the stronger the acid. The larger the pKa value, the weaker the acid is. We can also get this information off of a titration curve itself. The pH is where the concentrations of A- and HA are equal to the pKa value of your substance. It is what we call a measure of the proton binding affinity. How likely is it to hold on to that proton? What do I mean by this? Well, if we look at a pH curve, relatively speaking, pH curves should look something like this. And we would say this is our equivalence point. We know at the equivalence point that the concentration of HA is equal to the concentration of OH minus, not concentration specifically, I'm thinking of pKa now. At the equivalence point, the moles of HA are equal to the moles of OH minus. This is if we're titrating a weak acid, strong base situation. It looks very similar if you're titrating a strong acid, strong base. But we know at the equivalence point the moles of each are equal. They have been completely neutralized. And we don't have any HA and we don't have any OH minus in solution anymore. But halfway to that point is our half equivalence point. And we mean halfway. If your equivalence point was at 20 milliliters, your half equivalence point would be at 10 mils. At that half equivalence point, the concentration of HA is equal to the concentration of A- in solution. Why? Well, at the half equivalence point, half of the moles of HA have been converted to A- with the addition of OH minus. So, and they're all in the same solution. So at that point, the concentration of the HA is equal to the concentration of A-. They are present in equal molar amounts. At this point, your pH equals your pKa. If you remember your Henderson-Hasselbalch equation, pH is equal to pKa plus the log concentration of A- over HA. At that half equivalence point, the concentration of HA and A- are equal to each other. So this is like saying, the log of 1. The log of 1 is 0. What we're left with is pH equals pKa. But we say it's a measure of a proton's binding affinity. Basically, how likely is it for that acid to give up its proton or that base to accept a proton? Remember, acids want to give up their protons, bases want to accept protons. The difference is strong acids really want to give up their protons. Weak acids will give up their protons depending on if it's the right situation. Weak bases will take a proton if there's a lot of them floating around. Strong bases will take a proton until the last second that they have to give it up. So how tightly is it holding on to that proton? Okay, if the pKa of HCHO2 is 3.74, And the pH of an HCHO2 NaCHO2 solution is 3.89. Which of the following is true? So if the pKa is this, we know pH equals pKa at the half equivalence, which is when the concentration, in this case, of HCHO2 is equal to the concentration of CHO2. We know that, right? We know that our pKa is 3.74. We know that the pH is bigger than that at 3.89. So we know for sure that they are not equal to each other. But do we know what is present otherwise? Well, it is possible to make a buffer at this pH with these components. How do I know that? Because your buffer capacity is plus or minus 1 from pKa. So the buffer capacity for this system is 3.74 to 4.74. 2.74 to 4.74, plus or minus 1 from pKa. So it is possible to make a buffer at this pH with these components. So now I have to decide, is the concentration of HCHO2 a lot greater than NaCHO2? Is the concentration of HCO2 just greater than NaCHO2? Or is the concentration of HCHO2 less than the concentration of NaCHO2? Compare your pHs here. We are at a higher pH than the pKa value. At pKa, these two components are equal to each other. If the pH is higher, that means I must have more base present. If the pH was lower, it would be the HCHO2. If the pH was drastically lower, then we would have a lot more HCHO2. Since the pH is higher than the pKa value, though, we know we have to have more conjugate base present, pulling that pH up a little bit from the pKa value. What about amino acids? Another thing we need to talk about is amino acids. Amino acids are components that have amines and acids in the group, in the functional group. And you'll see this a lot in your other classes, organic chemistry, biochemistry, etc. But you need to understand when they have extra protons. When the pH is equal to pKa, there are equal concentrations of both forms, your acid and its conjugate base. When the pH is greater than pKa, there's a higher concentration of the basic form. And when the pH is less than the pKa, there's a higher concentration of the acid form. Let's look at glutamic acid, serine, and lysine. You should be able to predict the most common form of a given molecule based upon the solution pH and the pKa values of any acidic groups. So look at glutamic acid first. We've got 3 pKa's listed here, 2.19, 9.67, and 4.25. How the heck do I know what goes with what? Well, they're labeled here, and this labeling is supposed to help you identify it. The pKa of the alpha carbonyl here, the proton on the CHOOH, look at your compound. I know we don't write in carbons, but here's your carbons. And it says alpha CHOOH. What that means is the proton right here. The pKa at the alpha NH3 plus, that means right here. Now some of you may say, but it doesn't have a proton. We'll talk about that in a sec. And the pKa of the R group, that is the proton right here. Okay, so we have pKa values assigned. Now, why do I have NH2 written, but it says NH3 plus? It is a weak base. If the pH is low enough, there's a lot of extra protons floating around. That nitrogen has a lone pair. That nitrogen wants a proton if it can have it. So if the pH is low enough, this is going to have a proton around it, and this will actually be NH3 plus, even though we don't identify it that way in the base structure. In the basic structure, or the simple structure, not basic as in pH, but just the main structure of it, we're not going to write it as NH3 plus. But if there's a lot of protons floating around, it will pick one up. It wants that proton because it is a weak base. So although we don't write it that way, you have to recognize that that is going to pick up a proton. Now let's talk about how we're going to lose these protons. First, I'm going to erase these little carbons because they just distract me. Okay, so we've got 2.19, 4.25, and 9.67. I kind of think about it as like the buying power. How much is it worth paying for that proton? If the pH is below 2.19, the compound will pretty much look like this. Once we hit a pH of 2.19, half of this proton, half the protons on this specific site of the molecule is being removed. So if I have 10 protons, if I have 10 compounds, 10 molecules of this, 5 of them have lost this proton. Above a pH of 2.19, most of them, even more of them are losing this proton. Eventually, we get so high above a pH of 2.19 that this just becomes OH minus, and it loses its proton. It's going to lose it first. It's the least likely to hold onto it because it's the most stable. Now, if you look at the resonance here, and you'll get more practice with resonance structures in organic chemistry, but if you look at the resonance structures here, this is a very stable molecule. It can form the double bond to here and a single bond to up here. It can conjugate through here. It's a very, very stable molecule. So it's quite willing to lose that proton. Now I'm above a pH of 2.19. Let's say I'm at a pH 3. At that point, this is what my structure is going to look like. I keep increasing the pH, and eventually I hit 4.25. At 4.25, I've now removed half of this proton. I keep adding, and I am going to remove all of that proton. Let's say I'm at a pH of 5 now. All of that proton has been removed as well. But notice that NH3 kept its proton. Even though we don't write it in the original structure, it still has that proton because it wants it. It's a weak base. It really wants that proton until it can't really have it anymore. So we're going to keep increasing pH. We keep increasing. We go up to 6. We go up to 7. We go up to 8. We go up to 9. It still has that proton. We get to 9.67. Now half of them have disappeared. When I say disappear, I mean been removed. I shouldn't say disappear. Half of these protons have been removed. I go up to 9.67, and half of these have been removed. I go past 9.67, and the other proton has been removed, and this goes back to its neutral or base structure. This goes back to NH2. It doesn't lose another proton. It just loses the proton it had picked up because there were so many extras floating around in solution. There was a lot of extra protons before. It was easy to take one. Now we're at a high enough pH. Let's say we're at pH 10. And it loses that proton it's picked up. It's kind of like thinking about it in pH. How much did I pay this molecule to give those protons back to me? How much did I take those protons away until it finally said, okay, you can have this one too? And it gave it back. Looking at serine, I have the same thing. I've got 2. I've got the alpha CHOOH at 2.1 and the alpha NH3 plus at 9.15. Careful here. This is this and putting an extra proton here. So making it NH3. Look. Stop this. This is an alcohol. That cannot lose its proton. Not like this. It's not an acid. This is an acid. This is a carboxylic acid. Here is an amine. Those are what are going to gain and lose protons, not the alcohol. So 2.21. That means at exactly a pH of 2.21, half of those protons have been removed. Once I go above 2.21, say pH 2.5, 3, 4, the structure is going to look like this. That proton can be removed. That amine is going to keep that extra proton until I reach a pH of 9.15. Above a pH of 9, not at 9.15, half of them have been removed. As we get above pH of 9.15, they're being removed. Come to pH of 10, the structure will look like this. And lysine. So what is the most common form of serine at pH of 7? 7 looks like this, where the first proton here on the carboxylic acid was removed, look at lysine, I've got 3 here. Lysine, 2.18, 8.95, and 10.53. What you need to recognize on these is what's going to happen. This is going to lose a proton. This is going to pick up a proton. And this is going to pick up a proton. You see nitrogen, it's going to pick up a proton. So lysine, if I'm at a pH of, say, 4, is going to look like this. pH of 7, it looks like this. pH of 9, and pH of 11. Which titration curve is reasonable for the titration of a weak acid with a strong base? What do you guys think? Well, we've got titration of a weak acid, which means that the weak acid is is our analyte. The strong base is our titrant, which is what we add to solution. So by that definition, we know that the pH should start out low and increase. So we know it's not B and C. Now we've got A and D. Now we could say, okay, well, A is starting out about a pH of 1. D is starting out about a pH of maybe 2.4. So D is probably a good guess just because it's a weak acid, but you should also check your equivalence point. Your equivalence point is about halfway through this line. If I check about halfway through this line, and if I could draw a straight line, I see that the pH of the equivalence point is about 7. If I could do that here, the pH at my equivalence point is about 8. The equivalence point of a weak acid at equivalence. We have no more HA. We don't have any hydroxide or strong base. We do, however, have A-, has some concentration. Conjugate base. The pH will be higher than 7 because we have conjugate base present at the equivalence point because it's been produced by the neutralization of this reaction to produce the conjugate base and water. So D is our answer. Let's work 2 examples. 25 ml sample of HCl is titrated to the equivalence point with 14.94 mils of a 0.25 molar NaOH solution. What is the pH after only 10 mils of NaOH have been added? Well, let's see. We've got a strong acid plus strong base here. We've got 25 mils of HCl, 14.95 mils of a 0.25 molar NaOH solution. And I want to know pH after only 10 mils of NaOH was added. So first question I'm going to say is, well, what is the concentration of HCl? How do I find that? Through Stoich. Number of moles of HCl per liter of solution. I've got 0.250 mole NaOH per 1 liter of solution. And I used 14.94 mils of NaOH, so 0.01494 liters of NaOH solution. I know this is a 1-to-1 mole ratio, HCl plus NaOH, giving me NaCl plus water. So 1 mole of HCl to 1 mole of NaOH. And I know I used a 25 ml solution of HCl, so 1 divided by 20 or by 0.0 0.02500 liters of HCl gives me a 0.149 molar HCl solution. I also know then that means if I have 0.149 molar HCl and I use 25 mils of it, that I have 3.73 times 10 to the minus 3 moles of HCl. Need to set up a BCA table because I do have a neutralization reaction going here. So I'm going to copy this equation down for my BCA chart. I'm starting with 3.73 times 10 to the minus 3rd moles of HCl. And after I've added 10 mils of hydroxide, I've got 0.250 molar NaOH times 0.0100 liters of NaOH. That's 2.50 times 10 to the minus 3rd moles of NaOH. I don't have any salt to start, and I don't care, the water isn't going to change much. You always subtract the smaller of the two numbers, so minus 2.50 times 10 to the minus 3rd moles, minus 2.50 times 10 to the minus 3rd moles. Again, always subtract on the reactant side and add on the product side. We are always consuming reactants and producing products. The equilibrium expressions will take care of the rest for us. After, I've got 1.23 times 10 to the minus 3rd moles of HCl left, no NaOH, and I've produced 2.50 times 10 to the minus 3rd moles of NaCl. NaCl is a spectator, so I don't care, but I do need to know that I've produced it. Sorry, I keep hitting that button. Now I need to find pH. I have the moles of HCl I have in solution at the 10 mil mark. There's no NaOH minus left, so that moles of HCl is what's going to control the pH. But I need to figure out the new molarity. 1.23 times 10 to the minus 3rd moles. And at this point, I've combined 25 mils of HCl and 10 mils of NaOH, so 35 mils of total solution, which is 0.0350 liters of solution. That gives me a concentration of 0.0351 molar NaOH, or HCl, I apologize, which is the same as H+. Now I can go ahead and calculate pH, and I find the pH of the solution to be 1.45. So one thing that this means to is trying to reiterate for you guys is that even though I'm within 5 mils of my equivalence point, my pH is still very, very acidic because there's still a lot of strong acid around. It doesn't increase really drastically until we get near that equivalence point. How about this example? Hypochlorous acid, HOCl, has a pKa of 7.54. A 45 ml sample of 0.240 molar HOCl solution was titrated with a 0.25 molar standard solution of KOH. What is the pH at the equivalence point? Well, let's see what we got here. We know we have a 0.25 molar HOCl solution, and we have 45 mils of it. So 0.240 molar HOCl, 0.04500 liters, gives me 1.08 times 10 to the minus 2 moles of HOCl. I know that I use a 0.25 molar standard solution of KOH. How many moles of KOH do I use? Let's see. 0.240 molar HOCl times 0.04500 liters of the HOCl. That gives me moles of HOCl. And I know it's a 1-to-1 ratio because you can write out the reaction here, and I'll write that in a sec, but I see the 1 proton that'll be removed here. So times 1 mole of KOH to 1 mole HOCl. This gives me 1.08 times 10 to the minus 2 moles of KOH. I also will eventually need the volume here, so I'm also going to say, okay, but if I took this equation and continued it on and said times 1 liter of KOH solution to 0.25 molar, so 0.250 moles, this would give me 43.2 mils of KOH at equivalence. And yes, I cut some corners there. I converted to liters and then converted to mils in my head. If you're unsure, that would give you 0.0432 liters of KOH, and then I converted that to mils. So I know I've got HOCl, and it's reacting with KOH, K being the spectator ion, so OH minus. This is going to give me OCl minus plus water. I do need a BCA chart here because I have a weak acid reacting with a strong base. I know I'm starting with 1.08 times 10 to the minus 2 moles of HOCl. And at equivalence, I have 1.08 times 10 to the minus 2 moles of OH minus as well. I don't have any of my conjugate base, and water does not factor in. So minus 1.08 times 10 to the minus 2 moles minus 1.08 times 10 to the minus 2 moles. Those are both reacting, producing 1.08 times 10 to the minus 2 moles of my conjugate base. After the neutralization, I don't have any weak acid or strong base left, but I do have 1.08 times 10 to the minus 2 moles of my OCl minus left. Now I need to shrink this down because I'm not going to have room. Because I only have conjugate base left, I cannot use Henderson-Hasselbalch. I must use a Rice chart. I have OCl minus in solution. OCl minus is going to react with water. OCl minus is a base, so it will act as a base. It will produce HOCl, my acid, plus OH minus, acting like a base by pulling a proton by producing hydroxide in solution. I need the new concentration of OHCl, or OCl minus for the table. So I've got 1.08 times 10 to the minus 2 moles, and this was divided by a total of 45 mils plus 43.2 mils of solution. In liters. And I didn't write this out by individual numbers. I just put it on my calculator correctly. But the sum of that is what you're going to divide by, and you're going to get a concentration for your ice chart of 1.2 times 10 to the minus 4. And that is molar. Remember, ice charts are in molarity. We don't have any weak acid at the equilibrium because we've consumed it all, we've reacted it all, we've neutralized it all. And we have approximately no hydroxide because the only hydroxide present is just due to water itself. Minus x plus x plus x, 1.22 times 10 to the minus 4, minus x, and x. We're going to set up our K expression. Now, when you set up your K expression, note that you've got HOCl times hydroxide concentration in my numerator divided by OCl minus. Because I have hydroxide, I must use Kb. If it was hydronium or H plus up there, I would use Ka, but because it says hydroxide, I need Kb. I don't have Kb. Truthfully, I didn't even give you Ka on this equation, but I gave you pKa. So I can find Ka by undoing the pKa. Ka is equal to 10 to the negative pKa, which is 2.88 times 10 to the minus 8th. So Kb is equal to Kw divided by Ka, 1.00 times 10 to the minus 14, divided by 2.88 times 10 to the minus 8 gives you 3.47 times 10 to the minus 7. Now I've got my KB. And a very full slide. So this equals 3.47 times 10 to the minus 7. And it equals x squared over 1.22 times 10 to the minus 4. Again, we're going to assume that this value of x is really small, so insignificant we can ignore it. Solve for x. We find x equal to 6.51 times 10 to the minus 6. And this is equal to my hydroxide concentration. So you're going to find pOH, 5.190, 3 sig figs, 3 sig figs. And your pH from there, 8.810. So I hope the process made sense. You guys have done a lot of examples like these, but you should be able to calculate the pH at any point in an equivalence point, or in a titration, whether it be at equivalence, before the equivalence, or after equivalence. You should be able to figure out the pH. Work through these problems, work the extra problems, and I hope this helps.